Hello everyone, and welcome to this LangGraph crash course. In this course, you will learn everything you need to know to get started with LangGraph and to build sophisticated agents and workflows. We will start with the basics and then we'll build our way up to advanced concepts and components. And I'll explain everything using simple examples to convey the idea clearly. And at the end, as a final example, I will show you how to easily build a deep search agent using LangGraph. Now, for those of you who don't know what a deep search agent is, in my last video I showed how to create a hybrid deep search agent using LangChain for LLM calls and pure Python for orchestration. And I have discussed and mentioned in that video that we can build an autonomous deep search agent using a simple React architecture. And that's basically the final example that I will show you at the end of this course. But for more details about how deep search works or the difference between hybrid and autonomous agents, feel free to pause this video and go watch my previous one. Alright, so without further ado, let's get started. So first, what is LangGraph exactly? Well, LangGraph is a framework for building stateful, multi-step AI agents by composing LLM calls, tools, and control flow as a directed graph. Now I know that in this definition there is a lot to unpack, and we'll go through it step by step. But one thing to note before we continue, LangGraph actually has two APIs, a graph API and a functional API. But in this crash course, we will only cover the Graph API. So I said in the definition that we build AI agents with LangGraph using a directed graph. But what is exactly a directed graph in LangGraph and how do we define it? It's actually quite simple. It's a directed network of nodes connected through edges that define or dictate the flow of data, all while managing a shared state. A graph always starts with a virtual node called start. Then the start node always points to the first node you define in a graph, for example n1. n1 then points to the next node n2. So here these arrows are called edges. So here, for example, here we have the first edge and here the second edge. Then we can have something like a conditional edge. So from n2 we can go to either n3 or n4. So this is basically what we call a conditional edge. And then, for example, from n3 and n4, we come to the final node n5, and we have a virtual node for exit called the end node. So this is basically a very simple graph that we can define in LangGraph. And we have one more component, which is the state. So the state is like a dictionary and can be defined actually as a dictionary. It has key values and it's passed along the graph from the start all the way to the end. And in each step of the workflow, we can access the state to update it or read from it. So you can access it from each node, like so. And this is basically how you define a graph in LangGraph. Okay, so we have nodes, edges, and states. Now we need to understand these main three components. And to give you a concrete example for each component, let us first consider the simplified deep search workflow. So in this deep search workflow, we start with a user query. And in the planning phase, we break down the user query, generate a list of sub-questions and a list of web search queries. Then we perform web search to retrieve the list of URLs. Then we pass to web scraping to get the scraped data. And then we pass to data validation, we get the accepted data list, and finally we generate the final report. Now this is a simplified workflow, and for more details about each step and how to implement it, you can watch the previous video. So as I said, the graph is composed of three main components, the state, the nodes, and the edges. So now I'll explain each component and how do we define it. So we start with the state. The state actually is a shared object accessible across all nodes in the graph, and it captures the current state of your application. So to define a state, we create a class using a typed dictionary or a Pydantic Bayes model, and we define the suitable attributes for our application. So in case of our deep search workflow, we can define the first attribute, the user query, as a string. Then we can add the sub-questions as a list of dictionary, where each dictionary could contain the actual question, the web search query relevant to that question, and then we can add the URLs that we retrieved and the scraped content, and we can define other keys for our deep search workflow to work, but this is just to give you an example. So we can also add as a final attribute in our state the current question index. So this index would help the agent remember which question that is actually processing at the moment. And with these three attributes, we can define a complete state for our deep search workflow. Now, one more thing, we can have predefined states in LangGraph that we can use. For example, when building a chatbot, you can use the predefined message state that would keep track of the messages and append them to a list. Now, this is the definition of the state object and how you define it. Next, we have the nodes. So nodes are actually pretty simple. So a node is a Python function that encapsulates the agent logic. It takes a state object as input and returns a fully or partially updated state. It can also take a runnable config object as input, for example, to access the thread ID, and we'll see examples on that later on this course. So as an example of node that we can define for our deep search workflow, we can define a planning node that would generate the breakdown of the user query, the sub-questions list, and the web search queries. We can also define a web searching node or web search node that would get for each sub-question the list of URLs using the web search query generated. And we can also create a final report generation node that would get as input the accepted data lists and generate a referenced final report. And in nodes as well, we have predefined nodes. So we've seen before the start node in the graph that we defined over here. And it's actually a required node, so you can't define a graph without it. We also have the tool node, and it's a predefined node that is used in React Agent that is used to call the tools based on an LLM output. And finally, we have the end node that we've seen previously as well. So these are the nodes in LangGraph, and now we can move on to edges. So in simple terms, edges are components that decides the next node to run based on the current state, and they can represent fixed transitions or conditional logic. So as we've seen before, we have direct edges and we have conditional edges, and they can be used to define advanced patterns like routing or multi-agent architectures. And in our deep search workflow case, we can, for example, start with this edge that links the starting virtual node to the planning node. We can also have the final edge that connects the final report generation node to the end or exit. And from the graph that we defined above, we can, for example, create the conditional edge from node 2 to either node 3 or node 4. And we do so by connecting the node 2 to a routing function that we define, and that routing function would give us which node to go to next. And similarly to nodes and state, in edges we have predefined routing functions. For example, we have this tools condition function, and it is a routing function used in React Agent to decide whether to continue with the tool node or to exit to the end node. So these are basically the main components in a graph defined in LangGraph. There are other concepts and components that we can use to build more complex graphs. For example, we can define subgraphs, which are used for modularity to organize complex graphs into smaller reusable components. We have also checkpointers that are used for persistence to automatically save the entire state of our graph at each superstep. And what do we mean by superstep? Now, each sequential nodes are on different supersteps, and each parallel nodes are on the same superstep. So here we have 4 supersteps without considering the start and the end. So that's what checkpointers are used for. We can also use breakpoints, and these are basically used for pausing the graph execution, allowing for inspection of the state, and it's actually used for debugging. And we can also use interruptions. Now, these interruptions are used for the human-in-the-loop workflows, and it permits us to interrupt the execution and waits for a human to resume it. Now, there are several other components and design patterns that are very useful, but we won't cover all of them in this course. I've selected a few important ones in my opinion to not make this video any longer than it should be. Alright, so these are the basics that you need to understand to get started with LangGraph. And to create an application with it, we can do it like so. So we start first by defining the graph, then we compile our graph to get a compiled graph object. Now we can invoke the compiled graph object using an input, and then when the graph finishes its execution, we get the final state of the graph, or we can call it the output. Alright, so that's enough theory. Let me show you now how to use the Graph API. Alright, so here we have the Jupyter notebook for the LangGraph crash course. Let me first reconnect. The first thing you need to do is to set your Gemini API key. The Mistral API key is not a requirement, you only need it to run the final example for the DeepSearch React agent. So you just need to set your Gemini API key, and don't forget to give your notebook the access to this key. And then you can use this code to get your API key from your user data. Alright, so first we need to install a few libraries. We need to install LangChain, LangChain Community, LangGraph, Pydantic, and the Google Generative AI libraries for LangChain. Next, we need to import our API key. So first we will start with the basics. We will start with the state, nodes, and edges. And the first part is the state. And here you will learn how to define a state using either a type dictionary or a Bayes model to define its schema. And we'll also talk about the reducer functions, which are used to update the state from within nodes or other components. Alright, so first we need to import the state graph from the langgraph.graph. And this is the class we use to define our graph builder using the state we define. So as a first example, I'll show you how to define a state for a chatbot application using a type dictionary. And for that, we need these messages class from LangChain. So we're going to use a type dictionary, so we import it with a list type from the typing library. And to define a state, we simply create the class with the state name that you want, and we inherit from the type dictionary. Then you define your attributes. So here I said we're defining the state for a chatbot application, so we just need the messages list where we would store the messages between the AI and the user, and we can give it the type of a list of any message. And then we can initialize a state as such, so we can create our initial state using an empty list of messages, and we can print the type to see that it's actually a dictionary, and then we can print its content. And as you can see, we have an empty list of messages. We can also initialize the state using a dictionary. So here we pass a dictionary containing an empty list of messages, and we can verify that it gives the same result. Now, as you may know, we're using a type dictionary, which is defined using a type for each key, but this type is not actually enforced. So here we can define a state with wrong types. So for example, the first initial state here is defined using a Boolean for the messages, which is wrong. And then this second state is defined using a list of strings, whereas here we defined it as a list of any message objects. So these are wrong types here, but we can run this cell and we see that it is actually defined without raising any error. And that's because we're using a type dictionary. But if we wanted to validate the types for the inputs, we need to use a Pydantic Bayes model. So here we import the Bayes model with the field class from Pydantic. We create our class inheriting from Bayes model, and we define the attribute as a list of any message, and we can specify a default factory to initialize the messages with an empty list. So let's initialize the state first. We can initialize it without passing anything since we defined the default factory. As you can see here, we have a Bayes model object with an empty messages list. And then you can also print its content like so, or convert it to a JSON or a dictionary as such. And as you can see here, we have the content and we have the dictionary format for this object. Now to initialize a state with a different or a non-default value, we can pass a list of messages. For example, here we pass a human message saying hello, and we can print the output. So we have the initial state defined as such. And then let's say we made a mistake and we passed the wrong type for the messages attribute, and it should raise an error. As you can see here, we have one validation error for chatbot state Bayes model. The input should be a valid list, and we here passed a string. So as you can see, using Pydantic is much better for catching such type errors. Now, in both of these examples, where we defined the state using Pydantic Bayes model, or a type dictionary. We used the AnyMessage class for the list of messages. We could have used the base message class, but it is actually recommended to use AnyMessage for proper serialization and deserialization, as you can see from this part of the documentation. And that's why here we specified AnyMessage instead of base message. And when defining the state with the base model from Pydantic, you need to keep in mind that there are a few limitations. So the first one, as you can see, the output of the graph will not be an instance of a Pydantic model, and the runtime validation only occurs on inputs into nodes, not the outputs. And finally, the validation error trace from Pydantic does not show which node the error arises in. So these are known limitations for the Pydantic base model when used to define a graph state. One last thing you need to note regarding states: instead of a single shared data schema for all nodes, LangGraph lets you define multiple schemas. So one popular way to do it is to define a schema to control the internal data. This way we keep the intermediate information private between nodes, and then we define an input and output schema that would allow us to expose only the relevant data to external systems. And actually you can also define custom states for specific nodes, like for example here you can see we're defining a state for the node 2 input, and over here we're defining a state for the output of the node 1. And these are states designed for node 1 and node 2 to pass, for example, private data. Alright, so next we have the example where we define an input state, an output state, and the internal state. So here we have an input state, for example, the user input. We have as an output state the graph output. And then let's say, for example, for our internal state, we have only one internal variable, and we get the user input and the graph output. And then to define our graph builder, we create a state graph object. We pass the internal state and then the input schema and the output schema. So now you know all about how to define a proper schema for a state. Now let's move on to the reducer functions. Now let me show you first how a reducer function is defined. A reducer function always takes two variables, the old value and the new value, and outputs only one variable, which is the merged value. But you need to make sure, of course, that you have the right types. Now, the default reducer function overwrites the old value with the new value. So the default reducer function is defined as such. It takes the old value with the new value and simply returns the new value. Alright, so let's see it in an example. So here, when you define a state as such, we create, for example, this dummy state containing 3 attributes. For each one of these attributes, we have the default reducer function. And when you update the state, let's say, for example, from a node, and you update this first attribute, the old value for this attribute will be replaced with a new one. Now, to create a custom reducer function, you can simply create a function that takes, as I said, the old value and the new value, and returns only one value. So let's say, for example, for our dummy state, the first attribute is a float, so we create this custom reducer for it that takes 2 floats and returns the average value. Now to associate this reducer function to this attribute, we use the annotated class from typing. This way LangGraph will know that this is a custom reducer function for this attribute. And for the second integer attribute, we can, for example, define this increment reducer function, which takes the old value and the new value, and only increments the old value by 1, so it actually discards the new value. And as a final example, this attribute is a list of strings, and we can use the predefined add operation from the operator library to concatenate any new value with the list that we already have. So for example, here, let's say we have a list containing 2 strings. If we update this state with a new string for this attribute, that new string would be concatenated to this list, and the list would have 3 strings in the updated state. So this is how you define custom reducer functions and assign them to the state attributes. And with that, we've come to the end of the state paragraph. The next paragraph is about nodes. So here you will see how to define nodes and how to add them to a graph. So here we import the type dictionary, the state graph, and the add messages predefined reducer function. And we create the state as such. Now to define a node, we need to create a Python function that takes a state as input and returns a state. So for example, here this first node, we call it chatbot1. It takes the list of messages, which is the state we defined here, and returns a state object. So let's say here we simulate an LLM response, hello from chatbot1, and we can return the updated state as such. So we return dictionary containing the messages key, and we pass to it the LLM response in a list. So we need to put the LLM response in a list because we're returning a state object, which accepts a list for this messages attribute. And we can define the second chatbot as we did for the first one. So for example here, hello from the chatbot2. And to build our graph, we simply create our state graph object and we pass the state as we did before. And we can use the graph builder to add nodes. So we can add the chatbot1 and give it the name chatbot1. And this way we have a node called chatbot1 that calls to the function chatbot1 to update the state of the graph. Then we can add the node 2 for the second chatbot as such. And that's basically how you add nodes to your graph. Now, as you can see here, there are other options that you can use when adding nodes to your graph. So you can pass an input schema. And this is what we've mentioned earlier. You can pass an input schema specific to a node. And you can defer the node execution, for example, by passing defer equals true. And what do we mean by deferring node execution? So as you can see in this graph, we have two parallel paths. Now in this graph, the node B and the node C will be executed at the same time. But then we need also the output of the node B2. And that's why we need to defer the execution of the node D so that it waits for all the previous tasks to be completed so that we can run the node D properly. And that's why we need to defer the execution of certain nodes in specific cases like this one. We can also use caching for expensive nodes. And you can also specify destinations for edgeless graphs, but these are advanced concepts that we won't cover now. So now you can see we have a graph builder and we added a few nodes to it, but we still can't compile and run our graph yet because we need edges to define the flow of our graph and to connect the nodes. So if we run the compile method, you can see that we get an error stating that graph must have an entry point. Add at least one edge from start to another node. So as I mentioned earlier, to compile a graph, you always need a starting point, and that's what we see here. And that's basically what we need to know for now about nodes. The next paragraph is about edges. So here you will see how to define normal or direct edges, conditional edges, and how to specify entry and exit points. So to start with edges, let's import the start and end nodes from LangGraph. Then let's continue building on our previous graph that contains the chatbot1 and chatbot2 nodes. And we can add an edge that connects the start with the chatbot1. And to do that, we simply call the addEdge method from our graph builder. And we specify the start key, which is the starting node, and the end key, which is the name of the destination node. And this is how we define a direct or a normal edge. Now to define a conditional edge, we need a routing function. So let's consider, for example, this routing function that takes the state as input and returns a string. So if the length of the first message in our state is larger than 1000 characters, we return chatbot2. So we want to route the call to the second chatbot. And if it is less than 1000, then we return chatbot1. And to build our conditional or define our conditional edge, we use the add conditional edges method from our graph builder, and we specify the source node, which is here the starting node, and then we specify our routing function. Now, depending on the output of the routing function, the execution will continue along that path. A second way to define a conditional edge, when we have a routing function, for example, let's say it returns a Boolean variable. So let's say we define the routing function to indicate whether we use the chatbot2 or not. So if the length is bigger than 1000, we return true, we use the second chatbot, else we return false. And in this case, since it doesn't return a name or a key for the node to execute, then we need to specify a path mapping object that maps the output of the routing function to the names of the nodes to execute. And this way the execution would continue as intended. And that's basically how we define edges in LangGraph. Now that we know how to define and use states, nodes, and edges, let's see how we define, compile, and run a graph. So in this example, we need few imports. We need the annotated and list. We need the base model from Pydantic. We need the state graph start and the add messages reducer function. And we need from LangChain the AnyMessage class and the Chat Google Generative AI to use the Gemini model. So in this example, we will create a simple chatbot. So first we define the chatbot model. Here we're using the Gemini 2.0 Flash, and you can set the API key here. Then to create our graph, we start by defining the state. So here we call it message state, and it contains the messages, which is a list of any message. And we're using the add messages predefined reducer function. Now actually the state defined as such can be imported directly from LangGraph. So we can import message state from langgraph.graph. And let me show you its source code. So if we run it over here, so as you can see here, we have the message state. Here it is defined actually with a type dictionary, and we're defining it with the base model, but it actually has the same structure. So we can directly import it and work with it. Then we can define the chatbot node. So this time the chatbot would invoke the Gemini chat model and pass the state messages. So it would pass the list of messages and return the updated state. So here we return the response as a list, of course. And with this reducer function, it would append the new response to the messages list. And we can create our graph builder with a state graph. Then we add the node for the chatbot. And finally, we add the start and edges. And finally, we can compile the graph. Now, to visualize the graph, you can simply print the graph variable. And as you can see here, we start from the starting virtual node. We go to the chatbot, and then we exit through the ending node. And to run the graph, we can use the invoke method and pass to it the initial state with the user query or the user message. So here we pass a dictionary containing messages, which is a list containing the message from the user. So here the role is user and the content is hello. And let's run it. You can see that we have under messages a list containing the human message hello. And then we have the AI message, hello, how can I help you today? Now we can access the final message content as such, and we have the option to stream the output from our graph. So we can call the stream method, and we set the stream mode to values, which will emit all values in the state after each step. And this way the final step would be a generator. So as you can see here, when we run it, it's a generator object, and we can convert it to a list to see its content. You can see it's a list containing two elements. This is the first one and this is the second one. So the first one is the state containing only the human message, and this is the value that was emitted after the starting virtual node, where the graph populated the state or the empty state of the graph with our message. And then the second message is after the LLM was called. And as you can see, after that step, the reducer function added the AI message to our previous message. And that's how we get the full final state. Now we can use this generator object to print the messages in a streaming fashion. So for that, we have this print stream function. It takes the stream, and then for each state in that stream, it takes the final message and print it using prettyprint from LangChain. And here we use the time sleep to simulate the latency in response. So let's run this function. Okay, so we don't have an output because we actually converted the generator object to a list, and it's now empty. We need to run the stream again. Okay, so now we populated the generator again. So now we can see an output when we run the print stream function. And as you can see, we have the human message, and after a few seconds we have the AI message appear. And that's how you work with the graph invoke and streaming. Now these are the basics of LangGraph. You now know how to define a state with schemas and reducer functions. You also know how to define nodes and add edges. And finally, you've seen how to define, compile, and run a graph, and how to work with the output or final state object. Now we will see a few advanced concepts and design patterns. So in this section, we will cover 5 advanced concepts. We have the runtime configuration using runnable config. We have the command API for dynamic node routing and state updates. We will also cover persistence with checkpointers. We will also see how to use the MapReduce design pattern with the Sand API. And finally, we will see how to work with loops and how to modify recursion limit. So in my opinion, these are the design patterns and concepts that you need to learn to build more sophisticated agents and workflows. So we will start first with the runtime configuration. So the runtime configuration allows us to dynamically set parameters like the LLM model name or the system prompt that can be used within nodes and conditional edges without cluttering the graph's internal state. So sometimes we have variables that we want to use inside our nodes and conditional edges, but we don't want to include them in the state. And this is usually the case when you want to pass a variable that you set when you invoke the graph, and that variable would remain constant during the whole execution of the graph. Such variable you don't usually want to pass it in the state, and you can use this runtime configuration to pass it to the internal nodes and the different components of the graph. So in this example, we have the usual chatbot state. Then we define here a configuration schema. So in this config schema, we have only one attribute, the LLM model, which will indicate which model to use. So as you can see here, when we create our graph builder in the state graph, we pass the state and we pass the config schema that we've just defined. And let's say we want to use this config in this node, the chatbot node. So it takes the state and the config as input. Here the type is a runnable config because the config that we will pass later when we invoke the graph will be converted to a runnable config, and it should be defined using this schema. So when we get the config inside our node, we check for the LLM model, and in case it's equal to Gemini, we simulate, for example, this response, hello, from the Gemini chatbot. And in case we get an invalid or unsupported LLM model, we raise a value error. So that's basically how you use a runnable config or a config object inside a node. So we build the state graph, then we add the node, and we set the entry point and the finish point. So this is actually the same like we did before with add edge, start, and then chatbot. And similarly here with the set finish point, it's like setting the edge between the chatbot and the end node. And then we compile the graph. As you can see, we have the same graph as before. And now when you want to invoke the graph, you need to pass the initial state. And then we need to pass the config object. So here we always define the config object as such. It's a dictionary that have the configurable key. And inside that key, you can include any config variable that you want to pass. So for example, for the configuration with Gemini, we pass the Gemini option for the LLM model. And for the config with OpenAI, we pass the OpenAI option. Now, as you may have noticed here in the messages, we didn't specify the role to user and then the content to hello. And that's actually okay because we're using the add messages. So it will take care of that, meaning that it will convert this string to a human message object and it will append it to the initial state. So we can simply pass a string. So let's invoke the graph with both configuration and let's print the final message from both results. And as you can see here, we have for the first configuration, we have hello from the Gemini chatbot. And then from the second one, hello from the OpenAI chatbot. Now let's say we pass a configuration with the wrong LLM name. For example, here the name is Grok. And inside our chatbot, the Grok case is not treated. So normally this would raise a value error. And as you can see here, invalid or unsupported LLM model. So this is how you work with runtime configuration. The next thing I want to talk about is the dynamic node routing and state updates. It's actually the fact that we can update a state and specify the next step at the same time, and we can achieve that using the command class. So let me show you this example where we will use command objects inside nodes to replace conditional edges. So the node with the command object would update the state and at the same time specify the next step or the next node to execute. So first we need to import command from the LangGraph.types. Then we define the state, so it's a coin flip state where we have the result of the coin flip and the message we want to return. So let's say first we have a node for initializing the state, where the result is unset and the message reads ready to flip the coin. Now for the next node flip coin, it takes the state as input and returns either head action or tails action. And these are the names for the next node that we can run. So based on the coin outcome, which is obtained here using the random choice between heads and tails, if the coin outcome equals heads, the next node takes the value heads action and we update the message. And in the other case, where the coin outcome is equal to tails, the next node would be tails action and we update the message accordingly. Now in the return statement, we create a command object where we update the state and specify the next step as well. So the updated state contains the result of the coin flip and the updated message. And using the goTo parameter, we pass the next node name. Now one thing to note, when you return a command object, you always need to specify the node return type annotation. And as you can see here, we have this annotation command with literal options, heads action or tails action. And this is necessary for the graph rendering to tell LangGraph which node is accessible from the current flipcoin node. And then we can define the heads action node and tails action node. And here we update the messages with either we got lucky or better luck next time. Now we can create our graph builder. We add the different nodes that we defined. And then in the edges, we simply create the starting edge. And then we link the initialized state node to the flipcoin node. We don't need to link the flipcoin node to the heads action or tails action because they are connected through the command object. We simply need to connect the heads action and tails action to the ending or exit node. And finally, we can compile our graph and print it. And as you can see here, from the start, we go to the initialized state, then flipcoin, then we have a conditional edge. Now we could have defined this with a conditional edge, but I wanted to show you how dynamic routing works, and this way we obtain the same result. And finally we go to the end node and exit the graph. Now let's run this graph 3 times and print the output. As you can see, the first result is tails, so the message reads it's tails, better luck next time. And for the second and third run we got heads, so it's heads, we got lucky. And as you can see, it works perfectly, and this is how you implement dynamic node routing. Now the next part is very important. It's about persistence in the graph. So the concept of persistence in LangGraph is managed by checkpointers, and the job of a checkpointer is to automatically save a checkpoint of the graph's state after each super step. Now these checkpoints are stored within a specific thread, and that thread remains accessible even after the graph's execution is complete. So under persistence, I will show you 2 examples. The first one to teach you how to work with memory and snapshots, and the second one on how to work with interruptions. So in this first example, we will create a chatbot with memory and investigate its state history snapshots. So in previous example like this one, under the defining and compiling a graph segment, we've seen how to define a chatbot or how to create a chatbot and how to run it. But what's actually missing in this chatbot is that each time we invoke a graph, the state will be initialized with the message we pass to it. So that means in the second invocation, the graph won't have access to previous messages from previous invocations. And that's what we mean by memory here. So we're using a checkpointer to save the state of the graph that would be available under a thread ID even if we finish the graph execution. And the next time we re-invoke the graph would have access to that thread and can find previous messages. So here we define a chatbot as we did before. As you can see here, I didn't define a state. Instead, I'm using the predefined messages state, and then we set our LLM and our chatbot node, and we add our node and set the entry and finish points. Now when we compile the graph, we can use a checkpointer, and in this example, we're using the memory saver checkpointer that we imported from LangGraph checkpoint memory. And this checkpointer would save in memory a snapshot after each superstep execution. So let's compile our graph. And then when we invoke the graph, we need to pass a thread ID. And we do that by specifying a thread ID in our configuration dictionary. So as we did before, under configurable, we pass a dictionary that contains the different configurations that we want to pass to our graph. And to specify thread ID, you need to use this specific key. it is a predefined key that LangGraph would use to set a thread ID, and it takes a string value, so here we set it to 1, but you can set it to any value you want. And let's test our chatbot. So the first message I send is, "Hi, my name is Hamza," and we can print the messages using this loop. So as you can see here we have, "Hi, my name is Hamza," and the response is, "Hi Hamza, it's nice to meet you. How can I help you today?" Now we can ask the chatbot, "Do you still remember my name?" to see if it actually has the messages from the previous invocation. And to do that, we need to pass the same config that we've used, or actually we need to pass the same thread ID. You can, if you have other key and value pairs, you can change them, but you need to keep the same thread ID. Okay, so here we have the response. "Yes, Hamza, I still remember your name." Alright, so as you can see, with the memory check pointer, we can create a chatbot that keeps track of the messages from previous invocation. Now we've said that a check pointer saves a snapshot after each super step, and we can access the final state or the final snapshot using the getState method. So here we have the final state snapshot object, and as you can see, it contains the messages with other relevant information. And we can, for example, check few attributes like created at, which give us the time this snapshot was created. We can also find the next attribute, which give us the next node to run, and it's actually empty because this is the final state or the final snapshot. We can also check the values, and the values contain the final state of the graph after the execution finishes. We can also check the metadata to verify, for example, the thread ID. As you can see here, the thread ID equals 1. Next, we can also get the whole history of snapshots taken with this method getStateHistory, and we pass the config, of course. Now for each snapshot, let's print the values attribute and the next attribute, and let's run this. So here we have the different snapshot values with the next step printed. So actually it is in the descending order, meaning this first step printed is actually the last one executed. So to follow the chronological order of the graph execution, we start from the bottom. So as you can see, we start with an empty state, and our first node is the virtual start node. So the virtual start node would get the input and append it to this state. So that's why in the next step we have the messages populated with the human message, and we point to the chatbot node. So in the next step, this state would be passed to the chatbot node. And as you can see in the next printed statement, the messages contain the human message. And if we scroll, you can find the AI message after that. And the next node is the exit node or the end node. That's why we don't have anything. We are exiting the graph. And that's where the first invocation was finished. Now we start the second invocation. So when we start the second invocation, this time we don't start with an empty state. We start with the final state from the previous invocation. And if we scroll to the right, you can see that they are both the same state. So that state will be passed to the starting node to append the new user input. And then you can see the new user input in the next printed state. As you can see here, we have a new human message, and we pass it to the chatbot to get the final state. So that's actually how the graph execution works, and you can use this getStateHistory for debugging reasons, or to simply follow the execution of the graph to see whether it was executed in the intended way or not. Alright, so now we will move to the second part of persistence, and we're gonna build a chatbot with tool calling capabilities that calls for human assistance when needed. So in this example, we need to import the command class from LangGraph types with the interrupt function, and we need to import from LangGraph pre-built the tool node and the tool condition function. Next, we will build similar chatbot as we did before, but this time the LLM would have the capability to call a tool. So first we define the model. We're using, of course, Gemini. And then we create our graph builder using the message state. Next, we define the tool that we will bind it to the LLM. And this tool is used to call for human assistance. It takes a query as input, and it uses this interrupt function that we've imported to call for a human response. So we use the interrupt function where we pass the query that we get as input, and then we return the data that we get from the human response. Now what this interrupt action does, it interrupts the execution of the graph, and it waits for a human to resume the graph, and we can resume a graph, as we will see afterwards, using a command object that we pass to the invoke method, and you will see it in action in a bit. So after defining our tool, we bind the tools to our Gemini model. This way the model would be aware that it has this human assistance tool, and it would be able to call upon it when it needs or requires human assistance. Next, we define the chatbot node. So here it takes the message states, it gets a response from the Gemini with Tools model, and then it updates the state. Now, in case the Gemini requests a tool call, we need a node that would actually execute the tool, and that's what this predefined tool node does. So then we add the chatbot node and the tools node, and then we add the conditional edge that links the chatbot to either the tool node or the end node. So whenever the chatbot requests a tool call, this function would route it to the tool node. And if there is no tool call, it would route it to the end node, and we would have the response available. Finally, we add the edge between the tools and the chatbot so that the results from the tools get sent to the chatbot, and we create the starting edge. Now, since the interrupt function stops the execution of the graph and waits for a human to re-invoke it or resume it, then we need a checkpointer, of course, so that the graph can keep track of what has been done before in the previous invocation. And let's run this one. As you can see here, we start from the starting node, we go to the chatbot, then we have a conditional edge either going to the tools or exiting the graph, and in case the tools node was called, it returns the result to the chatbot. So let's test it with this user input. I need some expert guidance for building an AI agent. Could you request assistance for me? So here we're simulating the request from a user requesting human assistance. Then we set the thread ID in the config, and finally we invoke the graph to get the final state. As you can see, the AI message requests a tool call with a query, I need expert guidance on building an AI agent. So what happened here is actually when the tool node called the human assistance tool, it ran this interrupt function, and that's why the execution was interrupted. And we've got this as the final message. So now the graph is waiting for us to resume the execution. So we can pass this human response. We, the experts, are here to help. Check out Machine Learning with Hamza on YouTube for guidance. And we create the command object with the resume parameter. Now this is a different way to use the command object. Previously we used it for dynamic node routing, where we used the update and goto parameters. But now we have the resume parameter where we pass a custom state, and this state will be used by the tool or component that caused the interruption. So that's why here in the tool, you can see here we're accessing the data key from the human response. And that's why here we specified the state we pass with the data key. And then we resume the graph using the human command with the config object. So let's run it and see the result. And as you can see, here we have the previous messages with the tool calls. And as a final AI message, okay, the expert suggested checking out Machine Learning with Hamza on YouTube for guidance. Alright, so as you can see, it's pretty simple to implement the human in the loop workflow using the interrupt function with the command object. And it can be very useful. Let's say, for example, when creating a coding agent, you can use such workflow to make the agent ask for permission from the user, either to execute a command, or to search the web, or to perform any other functionality you want to implement. Now the next part is the MapReduce design pattern, and we can implement it using the send class or send API. It is very useful when you want to execute multiple tasks in parallel, and using the send object, you define a packet to send it to a specific node in the graph, and the packet you send contains the destination node and a custom state that can be different from the state you defined for your agent or your graph. And in this example, we will see how to use it to create a graph that uses MapReduce to calculate the square of each integer in a list. So for this example, we need to import the send class from LangGraph.types. And here let's define a simple state containing two attributes, numbers and squared. So the numbers will contain the input list of numbers, and then we will square those numbers and store them in the squared attribute. And here we specified the add operation as a reducer function for this attribute, so that each time we square a number in this list, we append it to this squared list. So we create our graph builder using our state, and then we add this node calculate square. So as you can see here, we can define node using a lambda function. If you want to define a simple function as a node, you can use lambda functions. So the lambda function would get a state as input, and what it does is it accesses the number key in that state, squares it, and then returns it in this dictionary to update the state of the graph. Now this state that we pass to the lambda function is actually a custom state that we will pass to it using the send class. So next we define this continue to squaring, which is a routing function. As you can see here, we're using it inside this conditional edge. So this routing function would return a list. This list is formed as follows. For each number in the state numbers list, it creates a send object that has the destination calculate square node. So the first part here, we precise the destination for this send packet. And then we create the custom state. So as you can see here, we have this key that is accessed in this node. So this function would return a list of send objects, each one pointing to the calculate square node, but with different custom state based on the integer from the state numbers list. So then we create the conditional edge from the starting point using the continue to squaring, and then we link the calculate square to the end, and we compile our graph. So as you can see here, the graph goes directly from start to end, and we have this calculate square as a separate node that is not linked to either the start or the end. But that's not actually what's going to happen when we execute it or when we invoke the graph, because for now we don't know how many edges are linking the start node to the calculate square. So for example, if we have a list of 3 integers, we would have here 3 edges between the start and the calculate square. So that's why this image is not really representative of the actual workflow that we created. But let's invoke the graph with this list of numbers and see the result for ourselves. Alright, so as you can see, the final state have the list of numbers and the list of squared numbers, and the values are correct. So what we've done here is that we mapped each integer from the numbers list to the calculate square, and then we get the squared list, but actually we didn't perform the reduce phase. So for example, to perform the reduce phase, we can add another node that, for example, adds those values or perform any other operation on that list. And that's basically how you implement MapReduce design pattern. Now, the final design pattern in LangGraph that I want to talk about is loops and recursion limit. In this example, we will create a graph with looping behavior between nodes. We have a loop state where we have an index with an increment reducer function that would increment this index each time it is updated. And this way we can track the loop's progress. And then we have the output data. Now we define the reducer function like this. So it takes both previous and new value, and it discards the new value and simply increments the previous value by 1, like what we've seen before. Then we define a simple node. It prints simply the state index, and it updates the whole state. And this is the only node we will use. The next function is used as a routing function. So this is like an exit strategy. If the state index is less than 30, we return continue. So we continue with this loop iteration node. And if the state index is bigger than 30, then we return AND to exit the graph execution. Now we build the graph, and then we add the loop iteration node, and we define the edges. So we set the entry point to the loop iteration node. Then we add the conditional edge. So we use the define should continue function. And in case it returns continue, we go to the loop iteration node again, and in case it returns AND, we go to the AND virtual node. Now we can compile our graph, and as you can see here, we start, then we have a loop from the loop iteration node to itself, and once we meet the exit condition, we exit to the AND node. Now let's invoke the graph and see what happens, and as you can see, we've got an error here, stating recursion limit of 25 reached without hitting a stop condition. You can increase the limit by setting recursion limit config key. That's what I wanted to point out. So sometimes the graph execution exceeds the recursion limit or the default recursion limit, and that can happen even if we don't have a loop, even if you have a complicated or a very long graph that takes, for example, naturally 30 steps to finish. This error would still arise, and that's why you need to modify the recursion limit for complex graphs and workflows. So here let's re-invoke the graph, and this time we specify in the config the recursion limit and we set it to 50. So as you can see, it runs perfectly and it stops when it reaches the step 30. Now in this example, we've seen how to loop from a node to itself, but this is actually redundant because usually you can replace it with a for loop inside the node. But what is actually more useful is having a loop between two nodes, like the loop we've seen in the previous example with the chatbot and the tool calling node. Alright, so these are the advanced concepts and design patterns that I wanted to talk about. Now before we finish, I will show you the last two examples that we have here, a React agent with human in the loop and the DeepSearch React agent. And since now you know all the basics and some of the advanced concepts that are required to build these agents, I will go through them much faster. So in this first example, we will create a React agent with human in the loop. And the task of this agent is to respond to frequently asked questions, and in case it doesn't have the response available in its database, it calls for human assistance to respond to the question. So to do that, we first define our LLM, then we define two tools. We have a tool for human assistance and a tool for frequently asked question responses. So this tool is used to retrieve the response for the frequently asked question. And this is actually a dummy example. In real application, you would have this tool have access to your frequently asked questions databases with the responses so that you can retrieve the accurate response. Now we create the list of tools and we bind it to the Gemini model. Next, we create our agent state and we create the tools by name dictionary so that we can access a tool by its name. And now we define the tool node. Now we can use the predefined tool node, and this is actually exactly how it is defined. But here, let me show you how it is actually working under the hood. So we get the agent state, we create the outputs list, then we loop over the tool calls from the AI, and based on the tool name provided by the chatbot, we access the tool using this dictionary, and we invoke it using the argument we get from the chatbot response. And once we get the tool result, we create a tool message containing the tool result as a dictionary. So here we convert it using JSON dumps. And then we specify the tool name and the tool call ID. And then we append this tool message to our outputs list. And this way we can update the state by the results from the tool calls requested by the chatbot. Then we define the node that calls the model. We previously called this node the chatbot, and its only purpose is to call the LLM and update the state with the response. But this time we're using a system prompt. So the system prompt states that you are a customer service assistant. You have tools that gives you access to frequently asked database and a human assistance. When asked about the company, always check with the frequently asked questions database first. And if no or unrelated answer is found, use a human assistance. Alright, so then we create the conditional edge. So we get the state. Then we see the final message from the chatbot, and if it doesn't have any tool calls, we go to the exit or the end node, and in the other case, we continue the loop. So now we can define the graph, we add the nodes for the agent and the tools, and then we add the edges. Now since we have the human assistance tool, which calls the interrupt function, we need to specify a memory. So here we create a memory saver object, and we pass it as a checkpointer. So now let's run this and print the graph. And as you can see, this is similar to the example that we've seen under interruptions. And then let's say, for example, we invoke it with the message, when was the company founded? And in the predefined answers we have here, we can find the answer, the company was founded in 2025. But the response we will get is a random choice between these two, either that or no answer found in the database. And based on the answer we get, we will see how the agent would behave. So let's run this one. So as you can see, first we said when was the company founded. The AI message requested a tool call to frequently asked question responses tool. and the tool message was no answer found in the database. So we got unlucky. So that's why the AI requested human assistance. But let's change the thread ID and run it again. Let's see if we get lucky this time. So we get the correct tool message. The company was founded in 2025, and the AI didn't request human assistance since it got the response. So let's then change the thread again. And we're changing the thread because we don't want to stack these messages. So it's like we're starting a new conversation. And let's ask it, who's the company founder? Alright, so in the tool message we get no answer found in database, and the AI requested human assistance. So it asked us, who's the company founder? We can create our human response. The company founder is Hamza. And we create the command object with the custom state. And then we resume the graph execution with the human command. Alright, so as you can see, the final message by the AI, the company founder is Hamza. And this is basically how you can create a simple React agent with human in the loop. You can add more tools and tweak it as you want to make it perform more complex tasks. But this is it for this example. The next one is DeepSearch React Agent. Now for this one, you need to install a few more libraries that are required by the tools that I'm using for this DeepSearch agent. And you need to set up Crawl for AI, then install Playwright. We need Mistral API key, so we need to set it over here. Now I won't go through the details of the different tools I'm using here. You can refer to the previous video for that. So here first we have a planning tool, which will generate a plan. As I showed you at the beginning of this video with the simplified workflow, we first generate a plan, so this is the tool that is used for that. Then we have the next tool that performs web search. After that, let's scroll down. Now all of these are helper functions, but we have this fetch and clean tool that would scrape a URL and clean the data that we retrieve. And then we have the judge collected data, and this is the data validator tool. And finally, we have the generate final report tool. Now we will use this list of tools in our React agent to perform deep search. So here we define the LLM that we will use. So here we specify a rate limiter because the graph execution is actually very fast and uses a lot of LLM calls. And if we don't use a rate limiter, we will always get a request per minute limit exceeds or some error like that. So here we set the list of tools. We bind the tools to our LLM. And here we have the system prompt that explains the different steps that the agent should follow to perform deep search, using these tools, of course. And then we can create a React agent using this predefined function. We just need to pass the LLM we use, the list of tools, and the system prompt. And LangGraph would take care of everything. It would define the state, the nodes, and the edges, etc. And this way we have our deep search agent created. Now we can pass a user query stating, for example, what are the effects of remote work on the US economy? And we can set a high or a very high recursion limit because, as I said, this workflow requires a lot of steps. So I set the recursion limit to a very high number. And as you can see, these are the outputs. It starts by generating a plan, then it searches the web for relevant URLs, and it filters out unwanted URLs. And then once we have the list of URL, we can start collecting data. So the agent calls for the crawl for AI to scrape data. And every time it scrapes a certain amount of data, it calls for the judge to judge whether the collected data to this point is sufficient or not to answer this question. And as you can see, the process takes a while. And then we can access the final report. So let me copy it. So as you can see, we have a detailed report with references everywhere, and at the end we have the list of references. And that's it. That's how the deep search React agent works. Alright, so I hope that was clear and informative, and see you in the next video.